the direct formula for the position of a pendulum is maybe not what you might think. Where does this circle come from?
Where does the circle come from?
It actually comes from the spring. The x-axis is position, and the y-axis is velocity.
So this is like two sine waves.
Yeah. Okay, this is now a simple pendulum. So it seems like the same thing should apply, right? You should see some sort of like circle. And it looks like a circle at first sight, but in fact, I'm going to now set it going like really high. Now you can see, whoa, it's not a circle. Something different.
What is that? At first I thought it was a parabola, but it's not a parabola.
Of course it's not a parabola. Otherwise it would spiral out of control. Because remember, the y-axis is velocity, and so it would have an infinite velocity in the limit. So I'm gonna explain this now. You'll normally learn that a spring moves in a sine wave, and so much so that the direct formula that you'll learn, not the differential equation, but the direct formula for the mass on a spring, the position of the mass on a spring, is basically just a sine function. But people often say that the same applies to pendulums. But that's actually just an approximation which only works if the pendulum is nearly at rest. And the direct formula is actually much more complicated. So much so that if you put damping into the mix, there is no known way to actually solve that differential equation, which means that there's no known direct formula to do it. So why does it work for a spring and not for a pendulum? I'll just quickly sketch out the spring setup. So this is the equilibrium position of the spring. Now, we're going to use two equations. So, for example, when let's say the position, we represent it as a little vector here. Let's say, in this case it's just the center, but let's say the position is this. Then the force is going to be, well, in the opposite direction. So that makes sense, right?
Yes, it does.
This is encapsulated in what's called Hooke's law.
Oh, I know Hooke. He was the greatest rival of Newton.
In fact, we'll also use Newton's law, but so we're going to use Hooke's law, which is that the force of a spring equals negative k, which is where k is just a constant, the spring constant, times x, which is the position of the spring. We'll also use Newton's second law, which is just, you all know this, force equals mass times acceleration. So we're going to combine these two equations together. So F is negative k times x, so negative k times x equals m times, and the acceleration is the second derivative, so the derivative of the derivative of position. So I'm going to write that as, so I'm going to write derivatives prime, so a second derivative is then double prime for taking the derivative twice. So this here is our differential equation for the spring. So can you think of any function that when you take its second derivative becomes its negative? Let's say k is 1 for now. So let's say sine. Derivative of sine is cosine, and the derivative of cosine is negative sine. Same for cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. Same for sine plus cosine. The derivative of sine plus cosine is cosine minus sine. And then the derivative of cosine minus sine is negative sine minus cosine, which is so all of these, if you graph them, you'll get basically just a wave. The sine wave you're used to. A cosine wave is basically just a sine wave shifted over, and sine plus cosine, well, it's basically just a distorted version of the sine wave. Now let's assume K is our spring constant to mass ratio is not 1. What is the thing? In fact, the answer is any constant times sine of the square root of the spring constant divided by the mass times time plus a second constant times the cosine of the square root of k over m times time. If you differentiate it twice, you'll get the same thing, but divided by k over m. You'll see that. So this is basically just our old sine wave, which you're all used to. Now let's move to the pendulum. Okay, so a pendulum, so we have the body right here, and it's going to be in this circle. We're going to represent position as the angle away from the vertical, which is going to be theta. And in the actual position, to get the actual position, we're just going to multiply by the length, which we'll call L. So L times theta is the position. There are two forces at play. There's the tension force, which is in the direction of the string. And there is the force of gravity, which is going to be the mass of the block times the gravitational acceleration. I'm going to break this up into two components: the gravitational force, the component that's parallel to the tangent, which I'm going to call g par, and the component that's perpendicular to the tangent, to the tension, which is going to be g perp. We care about g perp, that's our force, because if we cared about the original gravitational force, then the string would stretch. So we have the force, but this is the force applied to the angle, and we need the position, so we have to multiply by the length. And this is equal to negative, because otherwise it would move the other way, g perp. Well, what is g perp? Well, it's a matter of right triangles. If we draw this particular right triangle, we're going to zoom in on it. Mass, we have our mass times gravity, g par, and perp. And this angle is the same as this angle. So this is just theta. Now this is a right triangle. So sine of theta is the opposite, which is g par, no, G perp over mg. So if we want to figure out G perp, it's going to be, well, we just multiply both sides by mg. So mg sine of theta. So the length times the force is negative mg sine of theta. So the force is going to be negative the mass times g over L sine of theta. Using F equals ma, we can divide by the force to get the acceleration. So theta double prime is equal to negative g over L times sine of theta. Okay? This is a particularly juicy differential equation. More juicy than the previous one. We have to figure out a function, which if we take the second derivative, we get the function's sign. We can just about find an analytic solution. If we put damping into the mix, there's no known way to do it. So, why is it normally considered the same as a spring? Well, look, we have, it's based on the approximation that sine of theta is approximately theta for small theta. So if the block is really close to the center, so we would...
Like if the pendulum is nearly not moving.
Yes, then this would be the same as the spring. Then the formula would be correct. But if it's really far away out here, then it's gonna not really look like a sine wave. It's gonna look like something else. So that is why the direct formula for the position of a pendulum is not what you might think it is.
And this has been Science on the Balcony.